Hello. I'll just wait a few more minutes. Can you all hear me? Oh, that's interesting. That's a very big delay between when I said it and oh well. How is everyone now that it is Saturday of term 2 of week 10, meaning our term 2 has finished. How is everyone now that it is okay, my computer phone is very noisy. Hope you don't hear that. How about you? It's been stressful, I guess, because well, as we're approaching the end of the term, we've had a bunch of assignments, and then now got to prepare for finals. Okay, I think I'll get started then, since it's a few minutes past. So hello everyone, I'm Gordon, and I'll be presenting the first half of the MATH2801 and MATH2901 workshop. That is a revision workshop for, I believe, theory of statistics, which means the content includes a lot of statistics. I'll be presenting the first half, which is most of the probability theory, and John will be taking the rest of probability theory, as well as statistical inference, which is the stuff with the estimators, on Wednesday, I believe. I'm gonna turn off my camera. Okay, so let's just get started. as this is a bit of an introductory course, we start off with some basics. So just some basic definitions. Okay. So we define an outcome as a possible result of an experiment. The sample space is defined as the set of outcomes, of all possible outcomes, and an event is a set of outcomes. So these three, hopefully you should be familiar with from all your years of doing probability. Overall, I guess it's not too important. Once you get into the random variables and stuff, then you can kind of forget about this. But this is what underpins a lot of the probability theory. And sigma algebras are, I think they're a bit of a theoretical concept. So shouldn't be too important that you know that you're too familiar with that. So if you're not familiar with sigma algebra, it has to do with probability theory, but I don't think it's too important. A probability function. So when we find the probability of something, we're using a function which is a probability function, and all probability functions must satisfy these three properties. So in other words, all probabilities lie between 0 and 1. This you should be familiar with, hopefully. The probability of the sample space is 1. That means the probability of all possible events, of any possible event happening. So if we add up the set of all possible outcomes, then the probability of that happening is 1. And the probability of an event and its complement will add up to 1. So essentially, probability of A plus the probability of a complement should always equal to 1. With the probability function, we have the additive law, which states that the probability of A union B is equal to the probability of A plus the probability of B minus this intersection. Essentially, we're just adding the probability of A and the probability of B, and then since we counted this twice, we have to subtract it. If A and B are mutually exclusive, if you remember your set theory from discrete maths, this means that A intersection B is the empty set, and we define the probability of the empty set to equal 0. So if A and B are mutually exclusive, then the intersection is the empty set, and the probability of A intersection B is 0, which means that the probability of A union B equals probability of A plus probability of B. I want to change colors. I really like this blue. Okay. So a probability space is also known as probability triplet. It contains of three things: a sample space, a sigma algebra, and a probability function. Again, I think this is very theoretical, and for the sake of your final exam, this won't be too important, I assume. Next, we have the conditional probability formula. So conditional probability of A given B is defined as this: is the probability of A and B divided by the probability of B, given that probability of B is is not 0. What this means is that assuming B happens, what is the probability of A? And this comes up again later on in slightly different forms, but not in forms that are slightly appear different, but are really just this same principle. And the multiplicative law just comes from this. So if we move this over here, we see that probability of A intersection B equals the probability of A given B times the probability of B. And we can expand this into 3 events. So if we rewrite this as probability of A intersection B intersection C, we can do this, and then we just write it as, so first it's P A given, instead of B we have B intersection C times the probability of B intersection C, and this can be rewritten as this. And from that we have the concept of independence. So 2 events are independent if and only if we can write probability of A intersection B is equal to the probability of A times the probability of B. So essentially, if we go back to the formula, before we had probability of A, this is equal to the probability of A given B times the probability of B. So basically, if these two are the same, that just implies that probability of A given B is equal to probability of A, and likewise probability of B given A is equal to probability of B. And this makes sense because it just means that if A and B are independent, that means whatever happens with B, it doesn't change the probability of A. So when we take probability of A given B, we can ignore the B and just take the probability of A. Independence is quite important. It comes up a lot because we often assume independence. So we can make some nice approximations. And when we have to show independence, it always comes back to this. It always comes back to this form. Okay, that's a bit messy, but it can be written slightly differently, but it essentially comes back to this, where the probability of A given B is just probability of A multiplied by the probability of B. And so here we have a question from the past paper from 2018. And this is just testing whether we understood what I just talked about. So we have 2 events, A and B, and both of them have a probability that is non-zero. So show that if A and B are independent, they cannot be mutually exclusive. So in high school, when you were first taught probability, you might have been confused between independence and mutual exclusivity. But now, especially since we have the definition, hopefully you should know that they are different. And here we show that they're very different. So first, if A and B are independent, well, we just take what we know here. So if A and B are independent, then that means that probability of A intersection B is just probability of A times the probability of B. And because we have probability of A is not 0 and the probability of B is not 0, this means that this is not equal to 0. However, if we want A and B to be mutually exclusive, that means so if A and B are mutually exclusive, that means that alright, here, squeeze it in. A intersection B is equal, is equal to the empty set, and we know that the probability of the empty set is equal to 0. So in other words, since probability of A intersection B is not equal to 0, then that means A and B is not the empty set, and so they are not mutually exclusive. So now looking at part B, it asks if A and B are mutually exclusive, they cannot be independent. And actually, if you look closely, this is actually the contrapositive of part 1. So really, if we show part 1 is true, part 2 is true. And so we don't actually, part 2 doesn't actually add anything new. But anyway, for the sake of it, let's just do it. So we just have to go backwards. So if A and B are mutually exclusive, then probability of A intersection B is the probability of the empty set. Since there's no intersection, they are mutually exclusive. And we define probability of the empty set to be 0. However, if A and B are independent, then this must equal to probability of A, probability of B, which is not equal to 0 because probability of A and probability of B are both non-zero, since we know that from here. So here we have a contradiction, which means that A and B cannot be independent, and essentially we've proven the statement. And now for part 3, we have to show this statement. So we just, so here we use a conditional probability, so we just use the conditional probability formula, which was this one. So we just write it out. So A intersection A union B. Oh, okay, I wrote that wrong. Probability of A intersection A. Oh. A and A union B divided by probability of A union B. Okay. So if we look at the top half, using your set theory knowledge, or if you don't have, hopefully you remember from discrete maths if you did that, then this set A intersection A union B is essentially, we take A union B and take the intersection with A, that's just A, right? So this is just the probability of A. And now, I drew a U here. So by the additive law, this is P of A plus P of B minus P A intersection B. And since A and B are mutually exclusive, then this is 0, and we have what we wanted to prove. Independence can be extended to more than 2 events. So we say a set of events is pairwise independent if for any pair, so we take any two events, the probability of both of them happening is equal to the product of the probabilities. And now this is different from independence. So pairwise independence is not the same as independence. For independence, we need every combination of sets to satisfy this. Okay, I can't draw straight lines. So mutual independence, which is this second one, is stronger than pairwise independence. So what that means is that this is a more special case of the first condition. Law of total probability is this. So it says that if we're finding probability B and we know that A forms a partition of the sample space omega, so what that means is that if we have sample space omega, then we should be able to split it up into, say, A3 and A4. So we should be able to split it up into these sets such that it covers the whole, such that these A's cover the whole sample space and they do not overlap. And that's what it means by a partition. And then if we have a partition, then we can use this law of total probability. And using that, it's kind of like if we insert this into the conditional probability theorem, then we get Bayes' theorem, which looks like this, and is really just the conditional probability formula. So it's really just probability of A intersection B, probability of B. And now we move on to random variables, which is probably where most of the questions for exam will be based on. So what is a random variable? A random variable is actually a function. So the idea is that when we have these events, we want to convert them into numbers so that we can work with them and analyze them. So for example, let's say we have a coin flip, then the sample space is heads and a tails. Then we can convert this into a Bernoulli random variable where x is equal to 0 if we get a heads and 1 if equals tail. And in this way, this is why it's kind of like a function. Essentially, and once we apply a probability function, then these values will have a probability, at least for the discrete case. Notation wise, we always use capital letters to distinguish that they're random. So lowercase letters represent deterministic variables, which are not random. So then we have the cumulative distribution function, which is defined as the following. So one thing to note is that this sign is less than or equal to. So this is important in the discrete case because this matters, whereas in the continuous case the equality doesn't matter. So whether and if we want to find the reverse of that, so say we want probability of x is greater than x, then we just take the complement. Since this is the complement of that, then we just take 1 minus fx of x. And for x between y and x, then we use this. And one thing to remember, so sometimes you might forget whether this is less than or greater than. So one thing to remember is that f is increasing, and f of, I'm going to use some, hopefully you don't mind if I do that. So f of minus infinity should be 0, and at infinite it will be 1. And so this is to remember that f is increasing. And so if we compute, say f is greater than, say infinity, well that's 0 because that can't happen. So we know that capital F has to be less than, since f is an increasing function. So the properties, again, as I said, f is defined between 0 and 1, since it is a probability, with the limit at minus infinity being 0 and the limit at infinity being 1. So one thing to note here is that the cumulative distribution function is actually define for all x. So it's defined over the entire real numbers. So even if we have a distribution such as the exponential distribution, which is only defined for, or which only has probability for positive x, the capital F of x is still defined for all real numbers. It's just that we get 0 for negative values. So F is another properties. F is non-decreasing, so it can be flat, so it doesn't have to be increasing, but it is always non-decreasing. And F is right continuous. So for the sake of, so in discrete distributions, we'll often have a jump function, and so if it's right continuous, we know that means going from the right, it should be continuous, which means the top circles are filled in. But in this case, it's not continuous, as you can see. Discrete random variables are random variables which take a discrete number of values, so essentially a countable number of values. One thing to distinguish discrete random variables from continuous ones is that the values have mass, so we can find x such that the probability of x is not 0. And for continuous random variables, this is not the case. So that's what distinguishes discrete random variables from continuous random variables. With discrete random variables, we have a probability mass function, which is defined as just the probability of x equals x. So this notation is not always used. Sometimes people use p. I've chosen to use f because so people use p to distinguish it from the probability density function of a continuous random variable, but the two are actually quite similar in some ways. So that's why I still use an f. The difference being that this represents an actual probability, whereas, as we'll see, this one does not represent a probability. And the relationship between the cumulative distribution function is that fx, which is by definition the probability x is less than or equal to x, which is just the sum of all the mass functions. For a continuous random variable, we have, so if it's a continuous random variable can take a continuum of values. So as I said, so now for all x, we have probability. I'm using the writing p of x equals x will always equal 0 for wherever x is continuous. And this is just because there's an uncountably infinite number of values x can take, since if it is continuous. So instead of a probability mass function, since it doesn't have mass, we use a probability density function, which kind of shows the relative mass. So it shows for what values where the probability of x is higher. And here, instead of values, we look for regions. So often we might find what's the probability that x is within a region. So let's say A, between A and B. And to find that, we just integrate the density function from A to B. And now the connection, so here before we had a sum, but now since we have continuous values, we use the continuous sum, which is an integral, and you do it by summing from minus infinity to x. So going backwards, if we differentiate this by the fundamental theorem of calculus, we can see that if we take the derivative, that differentiating this, we get fx of x. So the density function is the derivative of the cumulative distribution function. So here I have another question. So we say that a continuous random variable is symmetric if x and minus x have the same cumulative distribution function. On the other hand, a density function is symmetric if essentially the density function is symmetric. So part 1 asks us to show that this show this statement. And note that we haven't actually, even though the question is about symmetric random variables, we haven't actually been asked to assume anything yet. The only thing we can do is just go by definition, so we do that. So what is f of minus x of x? So if you remember, the definition of a distribution function is just the probability of minus x, since that's our random variable, is less than or equal to x. And we can just flip the sign, since we're looking for a CDF of x without the minus sign. So we flip the minus sign and flip the inequality. And then note that see here we had probability of x greater than x is just 1 minus f of x. So we do that here. And note that here we have a greater than or equal to rather than a greater than. But since if we're dealing with continuous random variables, then that doesn't matter, since probably since this is equal to since this is equal to probability of x greater than minus x. So with that, then we just show the first part. And now the second part asks us that to deduce that if a random variable x is symmetric, then, or if and only if, the density of x, so the density is symmetric. So if x is symmetric, as I stated, then that means the cumulative distribution function is the same. So that means the cumulative distribution function of fx and f of minus x are the same. And so what we do, we use what we had before, and we plug it in. So before we had f of minus x, and so we just plug in f of x since we just want to look at x. So we have f of x equals to 1 minus fx of minus x. Now the question asks for the density function. So we differentiate to get the density function. So if we differentiate left hand side, we just get f. And if we differentiate the right side, we get fx of minus x. And this is what we needed to show, which is that fx is symmetric. And the question asks for if and only if, which means we also have to show the converse, although to do that we just reverse the steps, essentially. Moving on from there, we have expectations. So the expectation is essentially the average of something. If we just take the expectation of x, is the average of x. So in the discrete case, we just sum all possible values of x, p of x. Remember, we can also write this as the sum of x fx, since this is the same, this is the probability mass function. And the reason why I do that is that we can see the similarity between these two. But for the continuous case, we integrate instead. That way we're capturing all x. And often we denote this as mu, which is the population mean. What that means is that it's the theoretical mean rather than the sample mean. So it's the mean that comes from the theoretical distribution. Its expectation is a function. We don't just have to take it for x. We can take it on a transformation of on x, and what we do basically, we just replace this x. We just replace this x with whatever we had, so g of x. And note that this part is the same. So even though we're now taking the expectation of g of x, this probability is still the probability of x. So the only part we change is this part, and similarly we only change this part for the continuous case. And some properties is that so the expectation is the mean essentially of something. So if we take the expectation of a constant, well, a constant doesn't vary, so on average the constant will just be the constant. Expectations are linear, so this is because our expectations we get them from either summations or integrals, both of which are linear. So when we take a expectation of a linear combination, we can split it up. And this third case is only if x and y are independent, then we can split up this. So this is very important, that if we assume x and y are independent, we can do this. If we don't assume x and y are independent, then we can't do this. So this is so make sure you don't do this unless you know that x and y are independent. Moving on from x, the expectation, we have the variance. So before that was to show the mean. Now we have the variance, which is a measure of the spread from the mean. It's defined by this, and so one mistake that I sometimes make when computing the variance is forgetting to take the square. So what happens if we forget to take the square? So if we go back, remember the expectations are linear. So this becomes e of x, and then minus, so e of x is a constant since since it's the mean. So expectation of a constant is just the constant. So this is just e of x, which is 0. So that's the reason why we take this squared, because this would be meaningless. Often, so this is the definition, but often we actually use this second form, which we can get by expanding out this first form. And again, a mistake, a common mistake is that you might forget which one's first. So you might say, was it ex squared minus e of x squared? Whoops. However, if we look at the variance, if we look at the first definition, we're taking so in the continuous case, we're taking x minus e of x squared fx dx, right? So this is a square, so it's positive, and this is a density function, which is positive. So which means this variance will always be positive. So if you take this the wrong way around, you get a negative value, which tells you that you did it the wrong way around. So you can just do a sneaky switch and just remember, but try to remember that the correct form is this one. And often we also have the standard deviation, which is the square root of the variance. So often variance is denoted by sigma squared, and so the standard deviation is sigma, and it's the positive square root. So some properties of variance. So unlike the expectation, the variance is not linear, so we can't do what we did with the expectation, and that's due to this squared term. However, there are still some properties to know. So when we plug in an a, we get the a comes a constant a. So when we multiply x by a, then it comes out as a squared. So that means when we take the standard deviation of x, that's equal to, since the standard deviation is the square root, then we take the standard deviation of ax, and that's equal to a times the standard deviation of x. The variance of a constant is 0, and that makes sense because the variance is the measure of spread, and the constant is constant, so it doesn't have any variation. Right, so that's why it's equal to 0. This third one links variance with covariance, which is useful once you learn about covariance. It provides a nice way to calculate variance for more complex cases. If we shift the random variable by a, that doesn't change the spread, since variance is the spread around its mean. So if we shift x by a, we're just shifting the mean, but we don't change the spread, so that's why the variance is the same. And this fifth one is important. So if we take the variance of x plus y, we get the variance of x plus the variance of y, but also plus this covariance term. So this is not equal to variance of x plus variance of y. So again, x variance is not a linear transformation. So only when covariance is equal to 0, which is, I think, when x and y are not, I think when they're linearly independent, then this is equal to 0. So if x and y are independent, we can say that variance of x plus y is equal to variance of x plus y, and only, But it's important, if x and y are not independent, then most of the time this won't be, we can't cross out the covariance term. So here I have an example. Suppose that x is a continuous random variable with probability density function for f of x for x is greater than 0. And if you have a keen eye, you might notice that this is closely related to the normal density function, which is actually what we use for part 3. But for now, let's look at part 1. So part 1 asks us to compute the expected value of x. So here we can see x is continuous, so the expectation is just the integral of x times e of minus x. So x times f of x, right? And we can say from minus infinity to infinity, but we only have probabilities once x is greater than 0, so we can just integrate from 0 to infinity f of x dx. And then we just take f of x from up here and just plug it in, and then we just integrate. And actually, this can actually be done on R, which I have here. Right. So what we can actually do this on R. What we do is just define the function. So square root 2 on pi e to the minus x squared. That's what I have here. Square root 2 on pi minus e of x squared. I'll run this. So one nice thing about R is that you can run, even in the script, you can just run one, like a section. You don't have to run the entire script every time. So I can just run this, which creates the function. And then we want to compute the expectation, so we want x times f of x. So we create a new function, which is x times f of x. And we can just integrate this using the integrate function from 0 to infinity. Also, you might notice my eye is on dark mode, which you can, by default, doesn't look like this, but you can easily change it in the appearance. But anyway, so we integrated and we found 0.797 or whatever this is. Unfortunately, on R we can only do numerical integration, but often with the online exams, right, we just need to find it to nearest 3 decimal places. So in that case, then this is all we need to do. And we can verify. So our answer that we calculated by integrating it manually was square root 2 on pi. And we can see that we got the same answer, which is nice. Now part 2 asks us to compute the variance of x. So remember variance, we use the second form of variance. We know that it's just e of x squared minus ex. We can also have this form, the definition. But this is often harder to calculate, so which is why we use this. So first we just we already know e of x, which is what we did here. So we need to find e of x squared. Again, we just plug in x squared times the density function, and then we do the integration. This one's a bit longer, requires some integration by parts, but it's doable, and you end up with 1. And once again, we can also do this on R. So create the function. This time it's x squared times f of x, and then we integrate, and we get 1, which is what our answer was. And remember, remember not to stop here. So our question was to find the variance, which is e of x squared minus e of x squared. So we take 1 minus this squared, since this was e of x, and that's just 2 on pi. So this is our variance. So part 3 involves the normal distribution, which I haven't yet talked about, but this is a revision workshop, so I assume you guys should have learnt it. I'll go through it later, but for now, if I skip this question, I'll probably forget, so let's just do it. Okay, so let y be a normal 0, 1. So this is a standard normal random variable, and we want to compute the absolute value of y. So first, let's try to do that. So when you find e of y, well, again, by the definition of expectation, it's just the absolute of y times the density of y. And now we observe this. So we want to use what we found in part 1 and 2. And we might have noticed that this density function is similar to the density of a normal. And actually, we pull up the formula sheet, which you guys should have access to, because I think it's on Moodle for both courses, I assume. So on this formula sheet, we have, if you scroll down to the second page, we have all the distributions. So so we have so if you don't remember, you can take it from here. So so the density of a normal function is given by 1 over square root 2 pi e to the minus x squared, and this is for all x, so not just x greater than 0. And we notice that this function is even. So since this function is even and absolute value of y is even, we can make this transformation. Now we notice, so we have 2f of y, and we now notice 2f of y is equal to, so we plugging in 2 over here, we end up with 2 over square root pi, since 2 over square root 2 is square root 2 on the top. So we have square root 2 over pi e minus x squared on 2. That's 2 times f of y, which is equal to f of x. Okay, I don't know why it became an x. And so from that we plug it in, so 2f of y is just f of x. And now from this is actually the expectation of x, since even though the bounds are changed from 0 to infinity, we know that x is defined between 0 and infinity. So this is the expectation of x. And expectation of x, as we computed earlier, was square root 2 on pi, so e of absolute y is just square root 2 on pi. Okay. So now we've looked at the expectation, which is to calculate the mean, as well as the variance. So now we have the moment generating function. And the moment generating function is this function here. So basically we've taken the expectation, so for the continuous case, we take e t of x of f of x dx for all x, and then and essentially this is a expectation on x. So we take out, so once we do this in school, we integrate out all the x, and this is actually a function of t. But while we're integrating, this t is a constant. And we say that a moment generating function exists if there's a positive h such that mxt is finite for t within minus h and h. So essentially, we say that it exists if it is finite around 0. And what is the point of a moment generating function? Well, there's 2 points. Firstly, as the name suggests, we can use it to generate moments, which I'll cover on the next slide. But secondly, which is, this one is quite interesting, is MGFs are unique to a distribution. So if we have mx, so we have two, what this means is that if we have two moment generating functions that are the same, then actually it's only one way. So this, oops. So this implies that x and y have the same distribution. And the only reason why it doesn't work both ways is because not all distributions have moment generating functions. So generating functions, generating moments, how does that work? Well, firstly, what are moments? Moments are just it's just this. So the first moment is e of x, and second moment is e of x squared, and so on. And these are called non-central moments because they're not centered around the mean. But what we can do with this is that we can use them to find properties. For example, okay, the first one's already mean, but the second one we can use to find the variance, and the third moment we can actually use to find the skewness. And the way this works is that we take the moment generating function, and to find the rth moment, we differentiate it r times, and then we sub in t equals 0. And however, this only works if the moment generating function exists. So naturally, if we don't have the moment generating function, then we can't always do this. And if we look at the formula sheet, we can see that all these distributions have their moment generating functions. I guess in this case they will exist, apart from the hypergeometric one. Here we have two inequalities, so Markov's inequality and Chebyshev's inequality. This first one, I don't think it gets used that often, but this is what it is. And it's for non-negative random variables. Something to keep in mind. And the second one, Chebyshev's inequality, is something that does come up. Does get used. So essentially, both these inequalities, they don't find the probability, but they're used to find an upper bound for a probability. So here I have an example, which is apparently from the 2801 notes. I'm not actually sure if it's still in the notes because I got this from last year's seminar, but anyway. So we have a factory produces 500 machines a day on average, and that's very nicely presented to us. So we are told that the average is 500, and it is subject to a variance of 100. So they're pretty much just feeding us the information. And let x be the amount of machines produced tomorrow. So find the lower bound for the probability that between 500 to 600 machines are produced tomorrow. So both these actually provide upper bounds, but that's fine. You'll see that it fixes itself. So up here, you can see the Chebyshev's inequality. And so that's what we want to do. So we want to find the probability, or a bound for the probability that between 400 to 600. So if we write that in terms of numbers, that is just the probability that x is between 400 and 600, right? And we can rewrite this in this form as this. Right, so this is essentially between 600 and 400. And now we have it in this form. Although one thing to note is that, so our mean is 500, but here in the Chebyshev's inequality it uses the standard deviation, which is the square root of the variance, which is just 10. So this is actually 10 times 10, so k is 10. And then, I might have skipped a step. So this inequality uses the greater than or equal to, and this is less than. So we want to first take the complement, and this gets us in the Chebyshev form. And once we have that, we know that from Chebyshev's inequality, this is less than or equal to 1 over k squared, so 1 over 10 squared. And then if we rewrite this, basically it means it means 1 minus probability x minus 500 x is greater than or equal to 100 is Oh yeah, so that's less than equal to 10, 1 on 10, so that's okay, oops. So take 1 minus this, 1 minus probably x minus 500, less than equal to 100. We flip the inequality since we flipped the sign. Squared equal to 1 minus 1 over 10 squared. And so we get an upper bound, which is 1 minus 10, 1 over 10 squared, which is 99 on 100. So often with these, so sometimes they might not feed you these values. They might give you a distribution, and you might have to find the mean and variance from the distribution. But essentially, this is how they work. And on top of those two inequalities, we also have Jensen's inequality. I don't think this will be asked, but in case it does, if you have a function of an expectation and you need to find a bound, then I guess that would be when you would use Jensen's inequality. And now I think I've talked for a while, so I'll take a 5-minute break because I think I've talked too much, and I'll be back we'll resume at 4:10. So we'll take a break now. Okay, let's resume. So now we'll move on to talking about some distributions that we often have to come across. So with these distributions, they have different things associated with them. So there's a so distributions, they have a defined density function, and we can also find the expected value and variance and moment generating function with these formulas. So often with these distributions, even though there's a lot of stuff with them, it's good to be familiar with them, but you don't have to memorize them now since we have a formula sheet. Although with practice, I think you will get to remember them. And also, when computing probabilities, we can often do this using R. However, it's important to note that for some distributions, the parameters are defined differently. So when we're calculating, if you want to use R to calculate probabilities, it's important to keep in note the different parameters used when translating across. So first we have the Bernoulli distribution. And so I haven't written the density functions here since they're on the formula sheet. For now, here I'm just focusing on the intuition, so to help you remember what each distribution is used for. So we'll start with the Bernoulli distribution since it's the simplest case of the binomial distribution. And a Bernoulli distribution is the distribution which can take two values, so p of x can equal to 0 with probability 1 minus p and 1 with probability p. And that's the distribution of Bernoulli. So actually I've just written it here. It's used to model with an experiment with two possible outcomes, and we call one of them a success and one of them a failure. Which one is a success is up to you. So the word success doesn't actually mean anything. It's just that one happens with probability p and the other happens with probability 1 minus p. And a binomial distribution is a sum of independent Bernoulli random variables. If you don't want to think of it that way, essentially we're just choosing, we have n trials, and some of them are successes and some of them are failures. So each has so we're taking n trials which are all independent, and each one has the probability of p of occurring. Okay. The geometric distribution, actually going back here. So here I mentioned that often we denote q equals 1 minus p. That's just something that is often done for just to save some writing. It's not a new parameter, so we can use q even though q is not one of the parameters. And what happens is that, so for example, for a binomial distribution, we often write it as, it's f nx p x 1 minus p n minus x, and sometimes people just write it as p x q 1 minus x because they use q instead of 1 minus p. A geometric distribution, essentially it models a scenario where we want to count how long it takes until a first success occurs. So for example, let's say we keep rolling a dice until we get a 6, right? Then the number of times we have to roll that dice would follow a geometric distribution, assuming each probability is the same. Although one thing to note is that this is defined differently in R. So if we look at our formula sheet, we see that our density function is p1 minus p x minus 1. However, if we look at R, So if you use the help function, you can help using D or P. Actually, doesn't really matter which. So look at the help function, and if you look at this bottom right, we can see that they define the density as P 1 minus P to the X. And here it was 1 minus P to the X minus 1. So that's just something to be wary of. What's happening is that basically, in the case of a dice roll, suppose our first success happens on the third event. So in this case, this would be x equals 2, because we've had two trials until the first success occurs. But in R, this would be x equals 3, since we had 3. So that's essentially what's happening here. And there's also the negative binomial, which is a generalization of the geometric distribution, but I don't think it's covered in this course. A hypergeometric random variable models essentially it models the scenario where we're selecting balls out of a bag. And the difference, so this is a bit like the binomial distribution, except there's a limited number of balls, and essentially the balls are taken out without replacement. So I think this is what distinguishes this from the binomial. And again, this is something we have to be careful of. So it's in the on the formula sheet, we define the hypergeometric this way. So capital N is the total number of balls, M is the number of white balls, and N is the number of balls being taken out. However, if we look at in R, we can see that okay, that's a bit harder to read, but essentially, so here are the arguments. So M is the number of white balls, so that will be the same as our M. But here N is the number of black balls, which in our case would be capital N minus M. And then lowercase k would be number of balls drawn, which is our N. So that's something to be careful of if you want to do that in R. And finally, the Poisson distribution essentially models the rate of an event that occurs on average at a rate of lambda. So essentially, it's like the number of times something will happen. So say, so for example, we could model the number of buses that arrive in an hour. So suppose that the number of buses arrive randomly, then we could say the number of buses that arrive in an hour would be a Poisson, modeled by a Poisson random variable. And unlike the other distributions that we dealt with, the Poisson is not bounded above. So if we look at the distributions, the support, which is essentially values that they can take, with the binomial and hypergeometric, we see that they both have a maximum for x, but the Poisson and the geometric don't have this. Although for the Poisson, when x gets large, this becomes very small very quickly. And now we have continuous distributions. So firstly, the uniform distribution, which is quite nice. It has a constant density function, and essentially it means that the probability of essentially the probability is uniformly spread out. So basically, suppose so then our density function will look like this. It's a constant. And so basically the probability of any region, if it's the same size, then the probability will be the same. An exponential distribution is usually used to model the waiting time of an event. And one thing to note that for this course, for both Math2801 and 2901, the parameter used is beta, which is the scale parameter. So beta that should say rate. So in other sources and in R, we use the rate parameter. So here we can see that our distribution density has 1 over beta, e to the minus x over beta. And then if we go to our R, so we type in help, we can see that we use lambda, not 1 over beta, and lambda again here instead of 1 over beta. Essentially, in this case, beta is the scale parameter. It scales how spread out the variable is. So, on average, the exponential random variable will be beta. So the mean is beta. Whereas the rate is like the rate at which it happens. So, if buses come on average twice an hour, then on average you'd expect to wait half an hour for a bus. And a gamma distribution is the sum of exponential random variables. So again, we use beta in the second scenario, a second parameter, whereas in R they use the rates. And finally, we have the normal distribution, which is probably a very important one because we use it in the central limit theorem and in many other cases where we need to approximate things that have large samples. So normal has two parameters, mean and sigma squared, and that is just the mean and variance. However, one thing to note is that on R, again, so R does it differently. Is this one? So on R, they use the standard deviation instead of the mean. So remember to take the square root of the variance. The standard normal distribution is just the standardized version, and it's just we take a normal distribution, subtract the mean, and divide by the standard deviation. It becomes a standard normal. The reason why the reason why we used to care about this so much was because the normal distribution, the density function is given by this, which is not something we can integrate. So if you want to find probabilities of a normal random variable, we usually translate it into a standard normal, and then using a table of values which we calculated beforehand, we can then find the probability. And note that as we've done here, so if you take a linear transformation of a random variable, so in this case this is a linear since mu and sigma are constants, then you will get another normal random variable. And after that we have the beta distribution. Hopefully this won't get tested because it's a bit obscure, or it's a bit complex, I guess, when it has to use the beta function. But essentially this just models the distribution of proportions. So beta, I forgot to include, x is only between 0 and 1. So when doing this in R, there are 4 commands. So D something, so for example here, so say we want, so D gives the probability mass function or density function. So as I said before, the mass function and density function, which are for discrete and continuous random variables, are quite comparable. So R just lumps them into the same style of function. So generally for continuous random variables, we don't care about the density so much. But for discrete random variables, if we want the probability mass function, we need D. So for example, say we want to find, so say we have X binom, say 10, say 20, and then 0.2, and find probability X equals 1. Then we can just D binom, and so X equals 1, size, that's N, so 20, and probability is 0.2, and that will give us our probability. P is the cumulative distribution function. So that's something, so make sure you don't get tricked up. Even though P sounds like it stands for probability, it's probability distribution function and not the mass function. Q gives a quantile, so it's a reverse, which I'll go through quantile functions in soon. And R generates random value variables. And if you want to see the full list of distributions, you can type in help distributions, and this will tell us all of the available distributions, and then you can look into it. So here we have a question. So suppose the probability of hitting a target is 1 of 5 and 10 arrows are independently fired. What is the probability of the target being hit at least twice? So here they don't explicitly tell you what the distribution is, but so part of the problem is to determine what it is. So what distribution is this? So firstly, it's a discrete distribution, so because we can only have a discrete number of arrows, and the fact that there are 10 arrows independently fired, all with target 1 of 5. So you look at the parameters, we have 10 arrows and a probability of 1 of 5, and the arrows are independent, so that suggests that we have a binomial distribution with 10 and 1 of 5. What is the probability of the target being hit at least twice? Well, now that's easy. We know that once we know that X is less than or equal to X is a binomial 10 and 1/5 distribution, then we just plug it in. So remember our CDF is 1 minus this. Oh, okay, and this is 1 because, so this is just, we take the complement, this is 1p less than or equal to 1. And so that's why we use fx for 1. And we can do this on R, so 1 minus p binom, so 1, 1, and the n equals 10 and p equals 1 and 5. So if we run that, we get this. For part B, it asks the conditional probability that the target is hit at least twice, given that it is hit at least once. So if we remember our conditional probability formula, so it comes out often just in different forms. It's P, A, P, B. So the bottom goes there, and then we get the intersection of the two. And the intersection of these two, well, if x is greater than or equal to 2 and x is greater than or equal to 1, that's just the same as saying x is greater than or equal to 2, so we can take that out. And now we just do the same thing, so 1 minus fx 2, 1 minus fx of 1, which we can calculate using R. And now suppose we have a batch of 100 machine parts, which is inspected randomly by choosing 10 and testing them individually. If at most one is faulty, then the batch is accepted. So suppose the batch contains 10 parts. Find the probability that the batch is accepted. So this question also involves a bit of interpretation. So once we've understand the distribution, then the actual computing the answer is not difficult. So firstly, what type of distribution is it? Well, we only have a certain amount of machine parts, and we're selecting a bunch with assuming without replacement, since testing the same machine part multiple times is a bit pointless. So we find a random variable. So actually, we find a random variable. Let x be the number of faulty parts found, and we're told that we are selecting 10 parts out of 100 with 8 faulty parts. So selecting a total of 100 parts, so n equals 100. We know that. I want to change this. Okay. This was supposed to be 8. So suppose that there are 8 faulty parts, then m equals 8. And we are selecting 10 individually. So then this is our distribution. And then now we want to find the probability that the batch is accepted. And the batch is accepted if at most is 1 is faulty. So essentially x is at most 1. And this is just fx of 1, which we can do using R again. So this time, so if you remember the distribution, the parameterization for hypergeometric is different, so we have to keep in mind. So we're finding the distribution function at 1, q equals 1, m the number of whiteboards, so that's the number of faulty parts, which is 8. The number of blackboards, which is the number of non-faulty parts. Well, since we have 100 total, then that's 92. And then the number of boards drawn, we're drawing 10 boards, so that's 10. And if we run that, that is our answer. So QQ plots. Now that we've gone through distributions, we can compare distributions using QQ plots. And so first, a QQ plot compares quantiles. And the quantile function is just the inverse of the cumulative distribution function. So it's just if we have f of x is less than or equal to q equals p, then we can reverse that and say q of p is capital Q of p is equal to q. So basically, what is the value q such that the probability of x less than or equal? Wait, this should just be q. Okay, I'll fix that later. But essentially, it's just the inverse function. On R, as I showed before, so we had four functions. This third one is the quantile function. Quantile plots are they plot between two quantile functions. But we can do it between theoretical. Also, we can also do it. They're often used to compare a sample to a theoretical distribution to check if the sample comes from the distribution. So if the points lie on a straight line, that means the two distributions differ by a linear transform. So for example, if we have, so here I use the quantile function. So suppose we have the quantiles for a normal, and we generate some normal, we randomly generate some values from a normal distribution, but with different parameters. and then we create the QQ plot, we can see that it roughly is roughly a straight line. It's not exactly a straight line because these points are random, but we can see that it's roughly a straight line, which suggests that these two differ by a linear transform, which makes sense because we said that we take a normal distribution and apply a linear transform to it, it's also normal. So since we have two normals, they should be different. They should differ by a linear transform. However, this is exponential. However, if we try to do the same with a random sample of exponentially distributed values and create the QQ plot, we can see that it doesn't form a straight line, meaning that these two don't differ by a linear transform. And that's the point of QQ plots, is just to check if two distributions have that difference. Then we have joint density functions. So we have so this is just like a density function, except now we're applying it to two, or in this case, two random variables, although it can be more. And similarly to the density function, we have that they have to be non-negative. Total probability is 1, and if we want to find the probability, we just find it by integrating. Oh, okay, this is that's for the continuous case. We also have joint actually, let's just keep it to the continuous case. Why not? Okay, for the discrete case, then as you might imagine, it's similar. We just have f y equal to 1. In this case, sum of y in A yeah. And from the density function, we can compute the marginal probability function, which is basically the one-dimensional function, which is basically the one-variable function. It's called a marginal probability because we create it out of the joint density function. And to do that, we integrate out one function, one variable. I think this should be a partial derivative. But yeah, so basically we just integrate out the y for all values of y, so between minus infinity and infinity, and this should leave just a function of x, and this is our marginal density function. And this should be a proper density function, so it should follow the properties of a regular density function. For the discrete case, similarly, instead of integrating, we just sum out all the y values. Again, independence. So yeah. So if before we define independence as P A intersection P equals to P A P B, if we convert this into random variables, these two forms are not that different. But yeah, essentially for random variables, if this is true for all x and all y, then they are independent. So here we have a question from 2015. So we have a die and it has a die has 4 numbers on 4 faces, and we roll 2 of them. And however, instead of looking at the numbers, we define x to be the number of dice with 1 on the bottom, and y to be the number of dice with a 4 on the bottom. And since it says it's fair, we can actually calculate these probabilities ourselves, but here it's given to us, so that's nice. So part 1 asks to explain why fx1, 1, 2 is equal to 0. So that's x equals 1 and y equals 2, which is this one. So looking at the graph, we see it's 0, but that doesn't tell us why it's 0. So in order to answer this, we actually have to read the question. So what are x and y? It's the number of dice with 1 and the number of dice with 4. So this would imply that we get, so x equals 1 implies we have one die with 1 on its downward face, and y equals 2 implies we have 2 dice with 4 on the downward face. However, we're only rolling 2 dice, so we don't have 3 dice, so that's why this can't happen, and that's why it's not possible. Part 2 asks to find the marginal distribution function. So if we go back, to do that, we just sum out all the y for any x. So essentially, we just sum of the all the y's, so sum of the rows. So if fx equals 0, we sum that's equal to 4 plus 4 plus 1, 9 on 16. Second one is 6 on 16, and that's 1 on 16. And 0 otherwise. It's important to write these. It's important to have the cases so your function is properly defined. Part 3 asks, are x and y independent? It's not too hard to see that they are not independent. Why is that? So if we look at, we just have to compare these fx values to the table, right? So if x and y are independent, then the value of fx, so the value of fx shouldn't depend on y. Yeah. So for example, we see that f of x of 2 equals 1 on 16, right? That's what we have here. However, if we set f of x given y, f x and y of 2, that's this value, that's equal to 0. Which means if x and y are independent, then we have fx y x y equal to fx x f y y, and then this is 0. Okay. But essentially we see that fx given y, so if x equals 2 and y equals 1, we see that that's equal to 0, which is not the same as f of x equals to 2. Okay. And this means that if these two are not the same, that means the probability of x depends on y, right? Because if we set y equals 1, that changes the probability x equals 2. So that means they're not independent. Part 4 asks us to compute the mean, the expectation, and variance. So the mean expectation, we just sum up x times f of x, which is not too hard. We use the marginal density, so 0. So we take the values of x, multiplied by the probabilities, and we sum that up, we get half. And now to calculate the variance, so once again, we use this formula. So variance equals e of x squared minus e of x squared. And so we calculate E of x squared, which is the sum of x squared times the probabilities, which again we just sum this up and we get 518. And then we subtract the mean squared to get the variance, and that's your answer. Yeah, so the conditional probability is this once again. It's just so here, even though in the continuous case f is not a probability, we still have this formula. So this is true for both the discrete and the continuous case, except it's just that in the continuous case this is not a probability, but it's still true, the identity. With a conditional expectation, it's just the same as the regular expectation, except with our probabilities, we just insert the given y equals y. And actually the same with the variance. So nothing too remarkable. And one thing to note is that so the expectation of a random variable is normally a constant, but if we don't set what y is, so if we let y, we just say y is y and it's still random, then this will still be random and it will be a random variable depending on y. So with this, we've basically integrated out the x, but if we haven't said what y is, then it's still random on y. Covariance is a measure of the joint variability between two random variables. And actually now we can see that with this formula, if we plug in, so if we find covariance of xx, we can see x minus ex squared, and that's just the variance. So that shows what we had earlier. So some properties, if x and y are independent, then we have the covariance equals 0, since it is a measure of joint variability. However, the converse isn't true, so if we have covariance equals 0, that does not mean x and y are independent. So yeah, x and y can be swapped around. If you look at the formula, you can see it's not too hard to see why that works. And it's what the phrase? It was linear. Is it bilinear? Yeah, I think that was the term. But yeah, basically we can break up the covariance like this. And correlation is covariance divided by square root of the variance of x divided by square root of variance y, or in other words, covariance x y by sigma x sigma y. And this is always between -1 and 1 and tells us the strength of a linear relationship. Now notice that on the formula sheet it does tell you a little bit. So if a question asks for the strength of a correlation, I guess this is your guide. But yeah, so essentially a correlation of 1 indicates a perfect positive relationship, -1 indicates a negative relationship, and 0 indicates no linear relationship. So this is a measure of linear relationship, and yeah, so it basically measures how close the points lie to a straight line. Okay. And then moving on, we have the multivariate Gaussian, and this is a pretty ugly formula, so hopefully we don't have to deal with it. But essentially it's so as we're talking about joint distributions, we also have so joint known distributions such as the multivariate Gaussian or multivariate normal, which is basically just extending the normal. So instead of one variable being normally distributed, we have a vector of random variables being jointly normally distributed. And this goes into so now we're going to transforming random variables. So often we have, so a question might tell us that we have the distribution of x and y, and we want to find the distribution of a function of x and y. So this is one method, but I think it's more intuitive to use the CDF. So I have an example here. So question asks, compute the distribution of yn, which is defined to be the minimum of these z's, and these z's are an IID sequence of random variables which are exponentially 1 distributed. An IID, in case you forgot, stands for independent and identically distributed, and it's often an assumption that's used, and it's not something that you should ignore because it is important for our work. Okay, so I want to find the distribution of yn. So how do we do that? So we look at what it means. So yn is the minimum of z1 to zn. So that means that yn is less than or equal to all zi, since it's the minimum. And then using this we can incorporate it, right? Because when finding the distribution of yn, we have the probability that's equal to the probability that yn is less than or equal to y. But we don't know the distribution of yn, so we need to change it into the z's somehow. So what we do, first we flip it. This is a bit of a trick that you might not know, but here it is. So first we flip it so that we get a y that's less than yn. And now we said that since yn is less than or equal to z, then now if y is less than or equal to yn, that's less than or equal to zi, right? So we can rewrite that as the probability that y is less than all of these. And now if we go back, the z's were IID, so the first I stands for independent, which means we can split it up and into the different y's, and identically distributed means it's just the same thing to the power of n. Zi is exponentially distributed, so fz of y, so fz of y is equal to one on beta was 2, I think. Oh, beta was 1. Okay. So e to the minus 1. When e to the minus y, fz y 0 to y minus x dx 1 minus e to the minus y. Okay. And that's why if is this. And then once we once we simplify, then this is what we get. So moving on to part B, I should probably read the question first. Show that the probability density function of this new y, which is defined as n times yn to the power 1 of k, is given by this. Okay, so here we can use this previous theorem because we have a transformation of yn, right? So we define h y is equal to n. Okay, h is equal to n y 1 over k, and this is actually monotone for y is greater than 0. However, I think it's easier just to use the cumulative additive distribution function since this doesn't require memorizing. Right, so we go by definition. So even though we're interested in f in the density, we start with the distribution. So since we know the definition, so f of y is okay. First, it's probability that y is less than or equal to y, and then y we define it to be ny to n to the power 1 over k. So we plug that in, and then we move it across because we know the density. We know the distribution of yn, and we can do this because it is monotone, I think. And then this is just fyn of 1 over n y to the k. So we plug 1 over n y to the k in here, and then the n's cancel out, and this is our distribution. And now to find the density, we just differentiate. So differentiate, and we get this, which is what we needed to show. Part C is so part C, we want to find the expectation and the variance. I think I'll just skip over this since going a bit over time. But to find the expectation, we just use the formula. So it's just integral 0 infinity y fy dy. Since y is defined from 0 to infinity. And then this question was actually a bit tricky. This was last year, because you have to recognize, so you get this integral and you have to recognize that it's a gamma function, which is a little tricky. And you can't do it in R because we don't know what k is. And similarly for ey squared, we can get a gamma function, and so our variance becomes this. Oh, did I not number it? Okay, never mind. And now we move on to bivariate transformations. So suppose we have uv. So we know the joint density of xy. It's given by this, and we have a transformation u is equal to g1 xy, and v is equal to g2 xy. Then the joint density is given by essentially we just add this determinant, the absolute value of the determinant of the Jacobian, which is defined this way. And now this is the derivatives of x with respect to u and x with respect to v. So essentially our first step will be to basically inverse this function. Well, there's not quite an inverse because it's mostly variable, but essentially we need to find x and y in terms of u and v, and then we can compute this Jacobian. And this method can also be used, so even though this allows us to find u and v, if we're only interested in one variable, say u, we can still use this by setting v equals y. So essentially we just like have a kind of like a dummy variable. Okay, so you have a question where it shows that. So suppose we have a density function of x and y, and we want to find u and v. And nicely for us, they give us in the reverse form. So instead of u and v as a function of x, y, they tell us x and y as functions of u and v, which is actually better for us because we don't have to do any work. So all we need to do is find the Jacobian. So Jacobian is there. So we need to find dx du. That's just 1. And dx dv is also 1. dy du is 1, and dy dv is minus 1. So we get this. And the determinant of Jacobian is take the cross diagonal, minus 1 times minus 1, which is minus 1, then minus the off diagonal, which goes to minus 2. And so we take the absolute value to get 2, since our density function should be positive. So we just plug in so we just take our density function here, right, because we just take it and then we add our 2, so the 2's cancel out, so that 2 just goes out. And for x we sub in u and v, so x equals u plus v, so sub in u plus v, and y equals u minus v, so we sub in u minus v. And so this is our density function. Part 2 asks us to find the marginal density function. This is a lot of work because we have to integrate out v. See, I think I made a mistake somewhere because my final answer does not seem correct. But essentially what you do is you integrate out v, and the way you do that is, so this function doesn't have a known antiderivative, which means you just have to transform it into something that is the PDF of a normal, and we know that if we integrate a probability density function from minus infinity to infinity, then this will equal to 1, and we get our remaining function. The reason why I say it's not correct because it doesn't integrate to 1, which is something a probability density function should do. Convolutions is another method. It's specifically for finding the distribution of z equals x plus y. However, this method's not very nice because we have to do this integral, which often is not something we can do. I think for the sake of I think I'll skip this question. These slides will be uploaded, so you can read on the MathSoc website where there will be. And the other method is moment generating functions, and this is probably the nicest method of transforming random variables. Although it doesn't always work because the moment generating functions don't always exist. But when they do exist, and x and y are independent, then we know that mx plus y is equal to this product. And actually it's not too hard to show, so even if you don't remember this equality exactly, you know that mx plus y t equals to e of x plus y t of e xt e yt, and if x and y are independent, then these two are independent, which equals to e xt e yt, and that's the right hand side. So here I have a sample question. This one's it's not too hard. So I have two independent and identically distributed exponential random variables with parameter 2. So write the joint density function. So remember, because they're independent, we can say that fxy is equal to fx times f of y, and fx equals, so that's just so we go back to the formula sheet. The exponential is given by this, so it's 1 over 2 exponential minus 1 over 2x, 1 over 2 e minus 1 over 2y, and we just multiply them together and we get this. part 2, suppose we have w, which is the sum of x and y, and we want to find the moment generating function. So using what we had before, we just multiply them together. So moment generating function of x is here, so 1 over 1 minus 2, since our parameter is 2. So 1 minus 2t, and we just multiply them together, so, and because they're the same, then it's just this squared. In our general form, and part 3, determine the distribution of w. So as I said earlier, the moment generating functions are unique to distributions, and so we can, for this reason, we can use them to identify distributions. But the way to do that is not like straightforward. What you do is you just have to look through all of these and see which one it matches. To make our life easier, this is x and y are exponentials, so they are continuous, and so the sum of two continuous random variables would be continuous. So we don't have to look through the discrete ones. We know that w should be continuous. So we look at the continuous distributions and see which of these matches, and you can see that it matches this one. So so this is the MGF of a gamma, and then so we just compare the two. We see beta equals 2 and alpha equals 2, and so our distribution is gamma to 2. So we also have convergence in random variables. So there's four types of distributions that we went through. That is convergence in distribution, convergence in probability, convergence almost surely, and convergence in convergences. Oh no. Okay, I need to fix that. So essentially these four, they're just definitions, really. If you need to show it, then just pull out the definition. And they have a ranking, so we know that almost surely is stronger than probability, which is stronger than distribution, and convergence in LP is stronger than convergence in probability, and probably is once again stronger than convergence in distribution. However, we can't compare these two. We don't know which one is stronger. Okay, so here we have a question. So suppose we have this sequence, and we want to prove this is in converges to 0 in probability. So convergence in probability, if we look back, is this, right? So let's copy it down. Actually, I don't need to copy it down here. So we need to show this, and we need to show this for all positive epsilon, because that was in the definition, for all positive epsilon. And actually there's two cases. So we know that xn, even though regardless of the parameter, it has since it's Bernoulli, it has two values. So so you can take on 1 minus p. When you take on 0 with probability 1 minus p, you take on 1 with probability p. But anything else is actually it doesn't have any probability, right? So at most fx, so to show that xn is greater than epsilon, at most x is 1. So we split this proof into two cases. So first we look at when epsilon is between 0 and 1. In this case, so we apply this from the definition. then so the probability that xn is greater than epsilon, if epsilon is greater than 0, then xn can only equal 1, right? Since epsilon is less than 1. So this is essentially just the probability of xn equals 1. And we know this probability is just p, which in our case is 1 over n. And then once we apply the limit, that is 0. And now we look at the other case where epsilon is greater than or equal to 1. So if xn is greater than epsilon, well, xn can, as a Bernoulli random variable, at most it can take 1. So the probability of this happening is 0, regardless of what n is. So that means we've proven for both cases that this will equal 0. So in conclusion, we have shown that xn converges in probability to 0. Next we have the central limit theorem. So this is just, so what this is saying is that this is the important part. So xn follows this really what it can be summarized as. I mean, x has to be IID. So, but basically, when you take a sample mean of IID random variables, regardless of the distribution, this will eventually follow a normal distribution where the mean is the mean of x and the variance is sigma squared, which is the variance of xn divided by n. It's also written this way because, so this is written in terms of the standard normal, but now now that we have R, we don't have to convert everything into the standard normal, so we can just use this top form. So here I have a straightforward example. We have some IID random variables. We have a sample mean, and we need to compute this probability. So using what we did before, this is approximation because this is convergence in distribution, which means it's only normal when n equals infinity. However, as n gets large, it's close to a normal, so we can make approximations. So the mean, well, xi uniform 0, 1, so the mean is 1 over 2. And if we go to our formula sheet, we can see for a uniform distribution, the expectation is half a plus b, so 0 plus 1, which is 1 or 2. And then the variance is sigma squared, so here 1 on 12, 1 minus 0 squared, which is 1 on 12. And then divided by n, which is 48. And then now we just compute the probability. So here I changed it to a standard normal so you can see how that's done. But we don't have to do that. We can just, which is equal to f of x. So if we let say y equal that, then f of y of okay. So this is just 1 minus f of y 0.55, and we can do that in R. So 1 minus p 0.55, the mean is half, and these, so remember R uses the standard deviation instead of the variance, so we take the square root 1 over 12, 48. Run, and that's our probability. And we have the law of large numbers, which just means that the sample mean will approach the, basically just means the sample mean will approach the theoretical mean as as we take larger sample sizes. There's a weak law and a strong law, but difference between them is a bit hard to understand, and I think it's a bit technical. But yeah, so that concludes the my part of the seminar, and John will be taking the second half on Wednesday. So yeah, yep, good luck for your exam, and make sure to check out our other seminars, which will be held throughout next week.